Good day, young geometers. Happy New Year. So we are now on the second part of our discussion of sensed parallelism under the topic hyperbolic geometry. Recall that we already have discussed theorem 29H, assuring the existence and uniqueness of a sensed parallel line on passing through a point P, not on a given line, let's say L, meaning given a line L and a point P, there is always a unique line passing through P that is either right sensed parallel to L or left sensed parallel to L. Then theorem 30H assures that if, let's say, line L is right sensed parallel to a line M through a point P on L, then L must be right sensed parallel still to M through any point on L, meaning the right sensed parallelism of L does not depend on any particular point on it. It would be right sensed parallel at any point on it. Now we shall try this time to prove that left or right sensed parallelism is symmetric. Okay, so we have here theorem 31H saying that, or asserting that, if line L is right or left sensed parallel to line M, then M on the other hand would be right or left sensed parallel to L. So as I've said, this would mean that right or left sensed parallelism is symmetric. So here is the proof. Assume that L is right sensed parallel to M. So we have a line L, let's say this line is right sensed parallel to this line. So let us call this line L and this be line M. Then P be a point on L. So let's say this is a P point on L. So we can draw a perpendicular to line M passing through P. So let's say this point on M is called Q. Okay, so take note, this is right angle there by definition of perpendicular. Then we also consider a perpendicular to line L passing through Q. Okay, let's say QR be the perpendicular to line L that pass through Q. Now take note, if we assume that R is here, R, and this is perpendicular, meaning this is a right angle here, this is a right angle, we can show that this would lead to a contradiction, meaning this would be impossible, that R is to the left of P. In other words, if QR is the perpendicular to line L, R must be somewhere to the right of P. Why? By the exterior angle theorem. Note that if we name this point T, suppose there is another point T here. Note that angle QRT is an exterior angle of triangle QRP. In other words, angle TRQ or TRQ must have a greater measure than RPQ, angle RPQ. Okay, but then note that if we have here another point, let's say S, note that angle TPQ, this angle, let's call this red, color this red. This angle TPQ plus angle QPS would have a sum of twice that of a right angle. Meaning, this angle plus this angle would be equal to the measure of two right angles. But then, we have said that this cannot be a right angle. Why? Because this must have a measure of less than that of a right angle. Take note, TRQ is a right angle, so this must less than this must be an angle whose measure is less than that of a right angle. But both of them, or they combined, would give twice of a right angle. In other words, this angle must have a measure greater than that of a right angle. So that is angle QPS would have a measure of any greater than of any right angle. In other words, since this has a measure greater than that of a right angle, we can make a right angle here. Okay, because again, angle QPS is greater than a right angle, so we can make a right angle containing QP as one of its sides and P as the vertex. Let's call this point here Y. But again, by our assumption, line L is right-sensed parallel to M, meaning an angle or a line that would pass through, or that would be in the angle QPS must intersect line M, meaning this must intersect somewhere here. Okay, let's say at a point, let's just say J. Okay, so this is now a right angle. In other words, this is an interior of triangle QPJ. This angle here is an interior angle of angle QPJ. But take note that if we name this point here, let's say G, this angle PQG is an exterior angle of the said triangle QPJ. So this exterior angle, by the exterior angle theorem, should be greater than any of the interior angles, remote interior angles of the triangle, meaning this leads to a contradiction. Why? Because this is a right angle and it would have a measure equal to an exterior angle. So it cannot happen. That would be a contradiction. In other words, R cannot be here. R must be somewhere here. If we are to construct QR to be perpendicular to line L. Okay, so let us clear that out. Let's just construct another. So again, if we have a line L right sensed parallel to a line M, this L, this is M, and P is a point on line L, and PQ is perpendicular to line M. This is Q, and QR is perpendicular to line L by what we have just proven, that this point R must be to the right of P and not to the left of P. The right of PQ. Now let D be another point on M. So let D be another point on M, which lies to the right also of PQ. So it would be, to show that M is right sensed parallel to L, it would suffice to show that any line passing through or passing inside the angle DQP would intersect L. Okay, again, any line that would be inside this angle here, angle DQP, rather DQR would intersect L, the right side of R. So let that be, let's say, QE. Okay, so let that be QE. So let us now draw a line in that angle and call that QE. Let's erase that blue line. So let's say E is somewhere here. E. Let PF be the perpendicular to QE. So take note, this is QE. Let us draw a perpendicular to that line segment which passed through P. Okay. So let this point be called F. Perpendicular, so this must be a right angle. As before, the exterior angle theorem would guarantee that F would be to the right of PQ and not to the left of PQ, not here, not to the left but to the right. Okay, I would just like to discover that yourselves. Okay, again, the basis of that would again be the exterior angle theorem, just like what we have used earlier to show that R is to the right of PQ. Furthermore, as the proof state, PF would be shorter than segment PQ. Why? Because this is a right angle here, this is a right angle, and this is a right angle, so this is an exterior angle, meaning this would have a measure greater than this angle. This one. Angle PQF would be less than angle PFQ because these two are equal, both are right, and this angle is greater than this. Now, it is said in one of the propositions that in a triangle, the larger angle would have a longer opposite side than that of an angle with a smaller measure, meaning this PQ would be longer than PF. In other words, we can find a point somewhere here so that let's say a point, let's say given here, a point G, we can find a point G somewhere here so that PF would be equal to PG, meaning PF, this line segment, would be congruent to PG. Okay? Now, we can now draw GH perpendicular to PQ. So where is PQ? Here is PQ, that perpendicular to M. We can also draw a perpendicular to PQ passing through G. So we can draw a line here. GH, call that GH. So let's say H is somewhere here. Perpendicular to line PQ. Okay. Then let B be a point on L such that B is to the right of R. Okay, so B, let B be a point on L. So let's say B is here to the right of R, so that we have angle FPB. FPB. So, given this measure, angle FPB, considering the measure of angle FPB, this one, we construct angle GPI. GPI. So, there would be another segment from P to I, let's say here, so that this angle would have the same measure as this one. So this angle is congruent to this angle. Then I is somewhere, let's say here. Where is I? Then PI will intersect M at J. Why? Because note that angle BPI will now lie, or this line segment PI will now lie within angle BPQ. Okay, and since this is right-sensed parallel to M, then this line segment must intersect M somewhere here. So we can extend this so that it would now intersect line M. Call that intersection, said here, J. Call that intersection J. Now, since GH, segment GH here, intersects segment PQ at G. Okay? This segment intersects PQ at G, but it will not intersect QJ because this is perpendicular to PQ and M is also perpendicular to PQ, meaning they are perpendicular to the same line, PQ, meaning GH will not intersect M, in which case it will not intersect QJ. So this intersects this side of the triangle, but not this side. So by Pasch postulate, it should intersect the third side, PJ. Okay, so GH must intersect the third side of triangle PQJ, which is PJ. So there is an intersection here. Okay, let us call that point K. Point K. Next, on line PB, we can find a point L here, PB. We can find a point L so that PL would be congruent to PK. So take note, this is PK. We can look for a point L here on this line. Let's extend it a bit more so that PL, say, let us just assume L is here, so that PL will be congruent to PK. So let us mark those two congruent segments. So this segment PL is now congruent to line segment PK. And then we can construct FL by simply joining these two points. FL. So we now have two triangles PFL. Take note of that. Let us color that, let's say, green. Take note of the triangle PFL. I'm sorry for that. PFL and triangle PGF or PGK. Let us color that, let's say, violet. PGK. Okay. But take note, look at the two triangles. Let us make the size of the green triangle thicker so that it will be easier for you to see. Take note that in the green and the violet or purple triangle, they have two a pair of angles congruent, this angle of the violet and this angle of the green, a pair of sides. Let's say here we have PL and PK congruent, and another side PG and PF congruent, this side and this side. So by SAS congruence, we would say that triangle PGK rather, triangle PGK would be congruent to triangle PFL. So triangle PFL, take note that PFL is a right angle because that is congruent to angle PGK. Since this is right, this must also be right. This must be a right angle there. But we assumed earlier that PF is perpendicular to QA, meaning PFE is also a right angle. This is a right angle, meaning this line QE coincides QL, or FE and FL coincide here for that matter. So QE again, QE coincides QL, and since L is on L, line L, meaning QE intersects line L at point L. Hence, QE intersect line L, and therefore M is right sensed parallel to line L. Hence, proving theorem 31H. Next, before showing that sense parallelism is transitive, let us first show or prove a lemma. Okay, a lemma to be used in proving the transitivity of sense parallelism. So the lemma states that if M is right sense parallel to N, P and S are points on M, S to the right of P without loss of generality, and R is a point on N, then any line entering angle RPS will intersect N at a point T on the right side of R. Okay, let us show that. Again, we have M is right sensed parallel to N. So, let us say here is M. This is the figure for lemma, for the lemma. So this is M, and this is N, line N. So given that M is right sensed parallel to N, then P and S are points on M. So S is to the right of P, so P is here. Then S must be somewhere here. Then R, we let R to be a point on N. Okay, so R is a point here. So R can be here, or R can be here, or anywhere on line N. Okay, so let us just say R is somewhere here. So we have angle RPS. So any line entering this angle will intersect N at a point T to the right of R. So the point of intersection of a line within this angle here would be somewhere here. Okay, as stated in the lemma. Let us discuss the proof. Let U be a point on L below line M. So there is that given line, this line L, okay, which enters RPS. So suppose that line is this line L, and let U be a point on it, U. And let PQ be the perpendicular to N at Q. So PQ is the perpendicular. So in which case the placement of R can happen in two the position of R can then be categorized in two ways. It could either be to the right of Q or coincides Q. It is either Q or to the right of Q, or R is somewhere to the left of Q. So case 1, this is now our case 1. Case 1 in which R is to the right or coincides Q. Rather, Q coincides or lies to the left of R. Then clearly angle QPU, this angle would be less than QPS, this angle, because the whole is greater than a part of the whole. In other words, since M is right sensed parallel to N, line PU should certainly intersect N to the right of Q. So there would be a point of intersection here. That is by definition of right sensed parallel. Okay, it would be to the right of Q. Why? Because PQ is the perpendicular to line. So call that point T. But then, considering triangle PQR, it cannot be to the left, T cannot be to the left of R. Why? Because it is said that L must have to enter RPS. RPS, angle RPS, or all points in angle, the interior points of angle RPS are not interior of the triangle QPR. Meaning, line PU cannot contain an interior of the triangle, hence by Pasch axiom will not intersect the opposite side, the side opposite to the vertex P. In other words, T would be to the right of R and not between Q and R. Okay, that's by the hypothesis that PU should enter angle RPS. Okay, now case 2. What if R is to the left of Q? Case 2. So again, we have here M, which is right sensed parallel to the line N, and P and S are points on M. S is to the right of P, but R was happened to be to the left rather of line segment PQ. So R is here. Here is Q. Okay, so that is case 2. So again, this is a right angle. Then line L will either enter the triangle, because we are now talking, the angle concerned here is RPS. So L can be here or here. Okay, so L will either enter the triangle PQR. So L can be here, which by Pasch axiom will intersect segment RQ. If it intersects segment RQ, the intersection T will be to the right of R. Or line L can be it can enter here, which suppose this is the second case. When if this is not the case, if this is not L, so L must be here. So let again U be a point on L. So in which case, the measure of angle UPQ would be less than the measure of angle SPQ, and therefore would intersect again line N at a point T by definition of right sensed parallelism, and thus will intersect N, and that would be to the right of Q, hence it is also to the right of R. In which, in both cases, it would be true that the point of intersection T is always to the right of the point R. Hence, the lemma is proven. So we are now ready to prove the transitivity of sensed parallelism, either right or left sensed parallelism. Okay, which is called theorem 32H. If two lines are both right or left sensed parallelism to a third line, then they are right or left sensed parallel to one another. Two lines both right or left sensed parallel to a common line. Okay, let us move this first. But that can happen again in two cases. So case 1. There are two lines again in this theorem. There are two lines which are both right sensed parallel to a third line. So suppose we have L is right sensed parallel to N, and M is another line right sensed parallel also to N. Okay? So we shall show that L is right sensed parallel to M. So the first case is, what if N is between L and M? Meaning L and M are found opposite in the opposite sides of N. So in case 1, suppose we have here N, and L and M are in both in opposite sides. So here is L, and M is at the opposite side. Let us draw it a bit farther. So this is M. Okay, so that is for case 1. Clearly, M and N do not intersect since they lie on opposite sides of N. If they intersect, then they would tend to cross N because they are on opposite sides of N. Okay, if the intersection is to the side of L, M would have to cross N, hence it would intersect N. And the same case also if L is to intersect M at the side of M. So it would be therefore clear that they would not intersect. L and M would not intersect. Let P and S be points on L. Let P and S be points on L. So let's say P is here and S is somewhere here. S to the right of P without loss of generality. Then we construct PQ. Since P is not on M, we can construct PQ so that PQ is perpendicular to line M. So we can construct this line here, perpendicular to M. Call this point Q. But it would follow that PQ will cross N and will intersect N. Okay, because these 2 points, this segment rather, connects 2 points on opposite sides of line N. So the segment would cross N or intersect N at some point. Okay, let us call that point R. Let PU be a line entering QPS. So QPS is here. So let PU be a line that enters that. that angle. So let this point be U. It would then be sufficient to show that PU would intersect M to the right of Q. Okay? If we can show that this line would intersect line M to the right of Q, then we can say that L is right-sensed parallel to M. Indeed, that's what we need to show in case 1. But since L is right-sensed parallel to N, take note, this line L is right-sensed parallel to line N. Therefore, this line PU shall intersect, okay, because this is below, PU is not below line L, so this shall intersect N at some point. Okay, let's call that T. To the right of R. Okay? Since R is a point on N by the preceding lemma, then the intersection will be to the right of a point R on the line N. We can then construct line segment or a line joining Q and T. And let W be a point on N to the right of T. Say W is here. Then line PU, this line, would now enter angle QTW. QTW. So this line extended would now enter that said angle QTW. But then this line would now be below line N. But take note, M is right-sensed parallel to N, and hence by symmetry N would be right-sensed parallel to M, and therefore this line would intersect line M at a point to the right of Q, again by the preceding lemma. So it would intersect a point, let's just say Z, by the preceding lemma. Therefore, line PU was shown to intersect line M, and therefore L is right-sensed parallel to M. Okay, which is what we need to show in case 1. Case 2. What if this is not the case? This is not the case that N is between the two lines. So in case 2, we assume that M is between L and N. So here is M. And that is between L and N. Take note, L is right sense parallel to N. M is also right sense parallel to N. So we need to show that L is right sense parallel to M. Okay? So let P be a point on L. So let's say there is a point P on L. Suppose it is not true that L is right sense parallel to M. But Theorem 29H assures us that there is a unique line passing through P which would be right sense parallel to M. In which case, since L is not right sense parallel to M, then there is another line passing through P. Okay? So let's just move P here so that it would be on the line. So call that line O. Okay? Meaning there should be line O passing through P that is right sense parallel to N. Now, O is right sense parallel to M. N is right sense parallel to M. Hence, O is right sense parallel to N by case 1. Okay, if we recall case 1, this was L and this was M, and it was proven that L would be right sense parallel to M. But in this case, O is right sense parallel to M, N is right sense parallel to M. Therefore, O would be right sense parallel to N. Okay, but then P is a unique point. Hence, it was assumed that L is right sense parallel to N, and O is also right sense parallel to N. But Theorem 29H assures the uniqueness of such right sense parallel line through a point P, a unique point P. It cannot happen that there are two lines, both are right sense parallel to a given line through the same point. So there would be a contradiction. In other words, it cannot happen that L is not right sense parallel to M. It should be true that L is right sense parallel to M. Okay, therefore, if two lines are both right sense parallel to the same line, then they are right sense parallel to one another, showing that right or left sense parallelism is transitive, symmetric and transitive. Okay, so we shall end our discussion on hyperbolic geometry at that point. If you want to know more about the other topics, other concepts in hyperbolic geometry, you can read further about the topic. Okay, so we shall proceed to our next topic in our next video. That would be all for now. Thank you for your attention. Bye.